Okay, let's do some analytical IB questions. What part of the electromagnetic spectrum is used by H&MR spectroscopy? H&MR involves the nucleus of hydrogen atoms with the magnetic field, and that is associated with radio waves. That's pretty much all you need to know about the operation of the H&MR spec. What is always correct about the molecular ion M+ in a mass spectrum? The M+, the molecular ion, is just the molecule, and so the molecular ion has the same mz value as the molar mass, and the molar mass can also be called the relative molecular mass. So we're looking for answers like that. The M+ ion peak has the smallest mz ratio. No, has the highest. Mz ratio of the M+ ion peak gives the relative molecular mass of the molecule. That looks good. M+ is the most stable fragment. Not necessarily. Sometimes there are other fragments that are more stable and therefore give higher intensity, so it's not necessarily true. And the M+ ion has the greatest intensity. Not necessarily true. So that's the one that's the best. Which property explains why tetramethylsilane can be used as a reference standard? Now, this shouldn't be in your packet. This is an HL question, so let's skip that. 4. Which feature of a molecule can be determined from its H&MR spectrum? The number of hydrogen environments, total mass of hydrogen? No. Vibration frequencies of CH bonds? No, that's related to IR spec. Ionization energy of a hydrogen atom? Definitely not. So, answer is A. 5. Which molecule has an index of hydrogen deficiency of 1? So C6H6, that's way under, because it would C6H14. Then we have C2H6, also way under. We have C4H10, but because there's a nitrogen present, that's C4H11. So this one is in fact missing 2 H's and therefore an IHD of 1. Remember that nitrogen, the presence of the nitrogen adds 1 to the target. And then C2H6O, this one has a value of 0, so it's not any of those. 6, which compound gives this H&MR spectrum? Okay, so I can tell that there's 4 different hydrogen environments, and let's see, roughly, well, let's just start there. You can get into estimating about how tall they are to try to get a sense of how many hydrogens are in each environment, but let's see if we can just do it based on 4 different environments. So in A, I can see because it's symmetric, I actually only am going to have 2 different environments. These 4 in the middle and these 6 on the outside. In B, I can see there's 1, 2, 3 environments. In C, there's the middle environment and then the outer environment, so just 2. It's got to be D. 1, 2, 3, 4 environments, the ratio 3, 2, 2, 1, which looks like it could line up with that spectrum up there. What can be deduced from the following H&MR spectra? Looks like there's only 1 environment of hydrogen. There is only 1 hydrogen environment in the molecule. Doesn't tell us that it's a hydrocarbon, only carbon and hydrogen. Doesn't tell us anything about isotopes, and it doesn't tell us the number of hydrogen atoms. Okay, we're going to try questions 14 and 15. Okay. This is a mass spectrum of an unknown acidic compound, X, with empirical formula CH2O. Determine the relative molecular mass. That's going to be that heaviest peak. So that's going to be 90 grams per mole. And therefore deduce the formula of the molecular ion. Well, the molecular ion is just the molecule, but with a positive charge. So if our empirical formula is CH2O, it weighs 12 plus 2 plus 16, it weighs 30. And the molar mass is 3 times that big, so that means it's C3H6O3. So that's the molecular formula, and if I put a positive charge on it, that is the formula of the molecular ion. Deduce the formula of the fragment responsible for the peak at 45. If you use table 28, it will help you figure out some likely structures. They did tell us it was an acidic compound, and as soon as I know I have an acidic organic compound, I'm thinking about carboxylic acids. So pretty good guess that COOH is responsible, and because it's being detected, I know it has a positive charge. So I would suggest that is the thing that's creating the peak at 45. Deduce the formula of the fragment responsible for the peak at 29. Well, we'd have to probably try to sketch out more about this molecule. It is C3H6O3. So let's see. I think it looks like it has an index of hydrogen deficiency just of 1. So if we think that it has a carboxyl group in it, we've already used our double bond. So what I'm trying to figure out right now is where's that third oxygen? Wondering if it might have been an aldehyde or something, but I don't think it can be an aldehyde because we've already used 1 double bond. So that would be 1, 2, 3, 4, 5. That would give me 6 H's, but I need another OH, so there's probably an OH like here on the end, or maybe there's an OH on the second. I'm not entirely sure right now without a little more thinking through it. Let's see if there are any peaks of 29 possible. Well, CH2 weighs 14, and then O plus H weighs 17, so that would weigh 31. So that's not ideal. Let's see. If I get a carbon plus an OH group, then that might give me a peak at 29. So I could maybe suggest that there's a carbon, oxygen, hydrogen, something like that, like COH possibility as a fragment. We could also suggest something like, let's see, what other structure might be possible? If we had something like this. So I'm just kind of playing around with options. They haven't given me a ton here to go on. An HNMR would be pretty useful. So if I've already used my double bond here, then it's possible that I've made an ether group. And so now, even though it doesn't look like a very likely structure, I would have this group, which also weighs 29. So 29 is one of the groups that's in your data booklet. Or sorry, ethyl is one of the groups that weighs 29 in the data booklet. So I think either one of these, in fact, show up on the mark scheme, so you're okay. Okay, now we've got H in a Mars spectra, so we are looking at hydrogens. Simplified representation is shown, and then the relative peak areas telling us the numbers. So what's responsible for D? Well, probably a CH3 group, since it's got 3 hydrogens. And it shows up very low down in the chemical shift towards the right, which is where methyl groups tend to show up. Suggest a possible structure for X. So let's see. We want to put a CH3 somewhere. We want to put a COOH somewhere. That leaves us 1 more carbon, and then 2 hydrogens and an oxygen. So something like this is a possibility. You could probably come up with something else as well, but let's see. Yeah, if we go back, this one here wouldn't be possible because it's got 1, 2, 3 environments of hydrogen. So that ether one that I drew there wouldn't be possible. But now if I check here, I've got 1, 2, 3 environments of hydrogen that all have 1 in them. 1, 2, 3. This one way down here is clearly from the COOH hydrogen, and then I've got a group of 3 that is creating this peak at D. So I think this drawing is probably the best. Yeah, I think if you tried, if you don't get that on your first try, if you put the OH down here at the end, then the numbers are all off because you're going to have a 1 peak, a 2 peak, a 2 peak, and a 1 peak. So this ratio is different. It doesn't give you the methyl group. So from this part, you kind of know that there's a methyl. From the first part, we knew that there was a carboxyl, and then there was only so much that we could really do in the middle. Sort of had to put a C and an OH group. Okay, 15. Identify the analytical technique that would most readily provide the additional data required to calculate the molecular formula of X. Well, if I have the empirical formula, then I want a mass spec, because a mass spec is going to give me that molar mass, that mass to charge ratio. Okay, then I'm looking at the IR, information is below, deduce the information obtained from absorptions A and B. Well, A looks like an OH, and if we look carefully, it looks a lot like, you could probably get more specific, like hydroxyl in an alcohol, as opposed to a carboxyl, because a carboxyl shows up more in this region and the alcohol one shows up further down. That's what we can determine from A. And then B, well, let's see. B is a peak. It's right around 1700. It's not very sharp or deep. I'm looking at the mark scheme, and yeah, it looks like in the data booklet that is a C to C double bond, like an alkenyl group. It does not look like a C to O double bond. So the comment on the absence of any major absorptions here, yeah, we'd say that there's no C to O bond, because if there was one, I would see like a really deep peak here, like that. H&MR shows 3 peaks, relative area 211, deduce what can be obtained from this data. So that tells us, let's see, if we look back up, the molecular formula was C4H8. So there's actually 8 hydrogens, so that means that the actual, because the ratio is 2 to 1 to 1, that means it's actually 4 to 2 to 2. That's the number of hydrogens in the different environments. But yeah, this is just asking, do you know what that means? That's the ratio of hydrogens. So we've got to figure out something that has a carbon-to-carbon double bond and has an OH and has this ratio and is C4H8O. That's it. Yep, that's right. O2, sorry. Okay, and if we try to draw out some options, so I'll do some scribbles down here. Let's see, well, it must mean that with our O groups, because I can tell I've just got an IHD of 1, C4H10, so I've only got one double bond, and I know therefore that's got to be my C to C bond. That means my O groups need to be symmetric, because there's no hydrogen environment that only has one H. So like if I did an OH here, and then I do another OH that's not exactly the same, then they wouldn't show up as the same environment if I drew them like that. So instead, I need to make sure that this molecule is pretty symmetric. So what I mean by that is, oh, come on. Okay. If the OH is on the first and if the OH is on the last, now this and this H are the same because they're in symmetric positions. So I'm going to put the double bond in the middle, just as a pretty good guess. So now I've got this environment that has 2 H's in it. I'd have CH2 and CH2. Once again, those are symmetric. So then I have an environment of 4. And then if I have H's here to finish off those, I've got another environment of 2. So I'm going to suggest that that's the structure. And you don't need to know this. That's an HL topic. So this is a hard one, question 15. And I will leave question 12. If you get to that, give it a try. You have to do some functional group naming, some empirical formula calculating, molecular formula, IHD value, and then working with some data here to try to figure out structures. I think this video is long enough.